Today we have Valeria, who's going to help us make sense of classical and constructive logic together. Thank you, Valeria.
Oh, thank you, Sophie. Thank you for inviting me twice actually, to talk about that. To talk, you left me decide what I wanted to talk. And I kind of thought it would be nice to talk about logic again. I haven't talked to you guys about logic in a long time. I think I only gave one talk about logic in the Topos Institute, and that was in 2021 or something like that. And I think it's something that it's fun for something that Sophie's trying to do with the Berkeley Seminar, which is to make it more interactive, more about people talking to each other than just presentations. And I want to talk about ecumenical systems. And this work is with Elaine Pimentel and Luis Carlos Pereira. And Luis Carlos Pereira is a philosopher. So this work has lots to do with philosophy. And I'm no philosopher, so I'm not very good at the philosophical sides of it, but I think it's something that we can all discuss a bit. No worries, Bernard. And as I say, I want to have a discussion of this stuff, but there's some work written, so anything that's not very clear, you can read perhaps this is a conference paper in 2019, and then there's two journal papers, one in Synthèse and one in Studia Logica, that are about what I want to discuss with you guys. So, what is logic? I do not mean the rapper. Logic is a famous rapper. He's been retired for 4 or 5 years, but he's still very famous and still getting lots of money and stuff like that. And it's still the main hit when you ask about logic in Google. I'm actually talking about this guy, which does not get into the first page of Google at all. That's Aristotle. And as I say down there, Immanuel Kant, famous German philosopher, kind of famously claimed that Aristotle had discovered all there was to be discovered in logic. And lots of people more recently have kind of disagreed with that. So, but you might as well start from something that lasted more than 2,000 years, right? So we have around 2,000 years of Aristotle's laws of thought. And even that is a little bit controversial. People have different views on that. So there's some, people have different views on what are Aristotle's laws of thought. So Wikipedia, which is what I'm citing here, says that these are the 3 laws of thought of Aristotle. That every proposition implies itself, so everything is identical to itself. And of course, nowadays we're kind of disputing that very much, right? We are dealing with all this work on different notions of identity, different notions of equality to itself. He also says that the law on non-contradiction, that no proposition is both true and false, or nothing both holds and does not hold of any one thing at one time, which I personally like very much. And there is also this other proposition that every proposition is either true or false. Everything either holds or does not hold of any one thing at any one time. And that's the famous excluded middle. And that's something that since the beginning of the last century, the 1900s, has been very debated. So Frege, in the last years of the 19th century, so 1890s and stuff, kind of did a revolution in logic, because he kind of single-handed invented quantifiers and the symbolic notation that we tend to use nowadays for logic. But he didn't change the famous laws. He still talked about one true logic only, classical logic. But since then, things changed very much. And so this is the beginning of the 19th century, the 20th century, which is the 1900s, 1912 to be precise. And the change that I am interested in today are the changes to do with Brouwer, and for, I mean, the other person here is Lewis, C.S. Lewis. No,
Really not CS.
no, CS is the no, it's C.I. Irving, sorry, yeah, thank you. Because both of them have presented extensions, or in the intuitionistic case, rival of classical logic, which is intuitionistic logic. So I mean, the business about Lewis is a little bit more complicated because some people say that Aristotle already thought about this stuff, and that you know, if you're going to go back to real basics, he already had the modal operators and stuff like that. But Lewis, not the other famous Lewis, was the guy who actually wrote the formalization in a book in 1912. And Brouwer, as you know, questioned the validity of the principle of the excluded middle. And more recent.
Could you go back to your previous picture there?
Sure.
I've always wanted to make this assertion about Brouwer, to see how tough he looks there.
Wait, is Brouwer on the left or the right?
Brouwer is on the right.
That's
Yeah. I think my theory is he did all those amazing theorems in topology to prove that he was a mathematician. He really was a mathematician because he always wanted to do constructive logic, but he had to prove that he was a mathematician first. That's my theory about it.
Well, your theory has been confirmed, at least by Mark Atten. He wrote long pieces about that, and you know, which I read, kind of trying to prepare these things. He said that he actually started thinking about constructivity and then went and worked as a topologist, totally traditional topologist, proving the Brouwer fixed point theorem and lots of two other important terms about dimension, blah, 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 just so that he could be respected as a mathematician before he kind of came up with the idea of intuitionism as a foundation for mathematics, because he was not very fond of the idea of intuitionistic logic, which was actually formalized by Heiting, who was his PhD student.
Yeah, he didn't have like he thought the formalization was like kind of like missing the point, didn't he?
He did. Brouwer did think that the formalization was missing the point. But, you know, for people like some of us here that kind of come from a mathematical disposition, I think the formalization really kind of made it very clear what actually was under scrutiny. And, you know, that's a thesis that I would kind of want to, I mean, not about Brouwer and Heiting, but I wanted to kind of try to do a similar thing with this business of ecumenical logic, and the person who actually presented being Prawitz, Doug Prawitz. But you know, what we are trying to do, what I'm trying to do at least, is to see if we could do the Heiting to him and kind of come up with ways of formalizing and proving some of the assumptions and seeing exactly where things are or are not. But hang on the thought. You can ask about it in a little while. But good, we are having conversations. That's what it is about. So I'm not interested in intuitionism as a true philosophical person or a true intuitionist. And I actually had before a long quote from Dummett, who was a real intuitionist, saying that he was not interested in people who were eclectic, as he calls it, meaning people who wanted to be able to do proofs both as a classical logician or an intuitionistic logician. I'm much more pragmatic. I say a proof is a proof. I would prefer a constructive one, but if the only thing I can do is give you a classical proof, that's fine by me. And that's one of the big motivations for the ecumenical systems. So I think even classical mathematicians say this business that it's more convincing to exhibit a term T such that there exists an A, X of A is true, means exactly that A of T holds, than to say the double negation of it. It's not the case that for all X, not AX. And I am kind of starting from a precursor of this thing that I'm going to be talking to you about is Peter Krauss, who I discovered recently was a student of Dana's in Berkeley in 1966. But in 1992, Krauss kind of came up with a logical framework that helped identify where we have to use classical reasoning into a proof and where we can just be constructivist or be intuitionistic. And this thing is funny because it's not being published anywhere. It's a technical report from the university he was working on in 1992. And it's very difficult to find the second part of it, so I actually asked Professor Scott to give me a copy, but I think he didn't have it either, so I have only part one of this technical report. So let's kind of have a very quick motivation, mathematical motivation for being an intuitionist. So a simple theorem, there exists x and y not rationals such that x to the y is irrational. It's a simple enough theorem. And the proof, a very easy classical proof, goes like that. Consider square root of 2 to square root of 2. Well, as a classical person, you say to yourself, either A is rational or it isn't. If A is rational, then you can take square root of 2 equals y equals square root of 2, and then one to the up to the other is rational by definition, because you said if A is rational. And if A is not rational, then you can take x equals the A that we have, and y equals square root of 2. And then this very simple calculation here, that x to the y is square root of 2 to square root of 2, 2 square root of 2, that's square root of 2 squared, which is 2, which we all know is rational. And we all know, I didn't say it before, but we all know that square root of 2 is not rational. We know that since the Greeks, right? They proved that with their squares and stuff like that. So this is a simple proof, nothing too much to think about. And the classical mathematician says, oh, good, we are good, no problem. But the intuitionist looks to the proof and says, but hang on, is square root of 2, 2 square root of 2, rational or not? Which one of the two cases is the true? And I'm told that there is very sophisticated mathematics that proves that square root of 2 to the square root of 2 is not rational. But this beautiful proof does not let us know whether what is happening here, if square root of 2 is rational or it's not. And the intuitionists look at that and say, oh, come on, you're pulling my leg. This is not a good proof, because it's not really solving the issue for me or for the intuitionist. And the point of this system that Krauss first was a precursor of, and that I wanted to show you about, is to actually kind of combine proofs that are like that, beautiful little round things, but not very informative, with proofs that can be sometimes very ugly and long and stuff, but are constructive. You can find the algorithm that does it, and you can know what is it that you're getting at. So, kind of quoting from Peter Krauss, we should rather like to persuade the classical mathematicians to carry out their proofs, distinguishing between intuitionistic and classical logical operators, depending on what they actually prove. This way, their reasoning stays constructively valid and therefore preserves the possibility of a computational interpretation. So our reason for that is not philosophical. It's because you want to have the computational interpretation. We want to do things with those proofs. So Krauss is my first precursor, a second precursor already in 2015. So many years later is Gilles Dowek, who says that we should define classical connectives in quantifiers in terms of intuitionistic ones, because you can use this idea of Hilbert and Poincaré that axioms and deduction rules define the meaning of the symbols of the language. And it is possible to explain that some judge the proposition P or not P, because, okay, maybe I didn't say that before, I should have said, but one of the main differences is the excluded middle. But I mean, I did say at the beginning, right? That was one of the laws of Aristotle. So the proposition P or not P is true, and others do not, because they do not assign the same meaning to the symbols disjunction and negation. And Gilles goes on to say the need to distinguish several meanings of a common word is usually mathematics. Even something as trivial as there exists a number x such that 2x equals 1 is true or false, depending on whether the word number means for you natural number or real number. So the idea here is that if you want to kind of make sure that we know what we mean when we're using a word like number or when we use a word like disjunction, because the intuitionistic disjunction is very different from the classical disjunction. But Gilles carries on to say that instead of thinking about these different meanings of disjunction, you should think about, instead of saying that creating this judgment that something has a constructive proof or has a classical proof, you should introduce two symbols for each connective and quantifier. And for instance, you could use the symbol disjunction for the constructive disjunction and a symbol or little c for the classical one. And that might be better altogether. The same way as, if you say number, you should kind of, and someone says, is that 2x equals 1 is true for any number? You have to remember to say that which number you're talking about, if it's a natural number or a real number. Right. And I'm getting too long with my introduction, but that's the important point, is that that when we get to proof assistants and proof checkers, they are kind of used to formalize mathematical terms and verify software, notably critical systems, such as medical, industrial, and transport systems. And the development of these proofs, kind of, it's very big. You can't have little proofs, and you can't distinguish very clearly where, you would like to be able to distinguish in these big proofs where things are being classical and where things are being constructive. And having a system that could do both would be very helpful in kind of creating interoperability between different proofs and different proof systems. So this is adapted from Emilie Grienenberger, who was a student of Gilles Dowek, whose name I misspelled in the abstract. I'm sorry, kind of did the business of changing the ends here. So she's saying that the diversity of proof systems that one uses in these libraries raises the question of their interoperability. And we would like to be able to have proofs in one system be easy to recheck in other systems. And for that, you would like to have interoperability on the level of the logic itself. Okay, so I hope I have convinced you that adding different versions of the connectives and quantifiers is a good idea. And I will kind of concentrate from now on in one particular proposal, which is the proposal of Doug Prawitz in 2015 in this paper that he called Classical versus Intuitionistic Logic, which appeared in a book that is probably not very well known and hasn't got many citations because it's from a small printing company in the UK, Dovgabai's printing company. And hence, lots of people haven't heard much about it, about this proposal of Prawitz. So what is Prawitz's proposal? Prawitz is a philosopher, so he spends lots of his paper explaining philosophically what he's trying to do. And he says that my interest in logic is first of all an interest in deductive reasoning. The so-called, because he's famous as a proponent of intuitionistic logic, but the so-called classical first order predicate logic is an attempted codification of inferences occurring in actual deductive practice. And he says, Dummett dismisses an eclectic attitude that finds interest in both classical and an intuitionistic codification, but that's exactly what Prawitz is doing here. He will do. And I don't think I'm going to go through that many of this of Prawitz's quotes, but you know, the main point that he's trying to make, I think, is about his theory of explanation of the meaning of connectives, which is something that I thought you'd like, Chris. So that's some of the quotes we're thinking of you. Brandon is even mentioned in some of this.
So is he basically trying to argue that if you don't have like strong normal forms, then you don't?
I think he's trying to come up with the notion that canonical proofs or normal proofs are an important component of the meaning of a connective.
Sure. I just mean, like, I feel like it's...
But he's doing something else that I'm not very much in agreement,
Yeah,
which is that, I mean, as a mathematician, I do not want to be thinking about what is the meaning of something. I want to see, when I kind of codify things, what are the consequences I can get out of it. So kind of hold the thought again. We'll come back to that in a little while. So his point on this conclusion is this business that the relationship between intuitionistic logic and classical logic is a little bit more complicated than you might think. You know, everything that's proved intuitionistically is proved classically as well, but it's not true to say that classical logic is stronger than intuitionistic. Instead, he wants us to say that intuitionistic language is more expressive than the classical one, having access to stronger existence statements that cannot be expressed in classical logic. And then he says, but there's no need to choose between the two codifications because we can have a more comprehensive one that codifies both classical and intuitionistic reasoning, but based on a uniform pattern of meaning explanations, which is, I think, what you're trying to get at, and that's what Prawitz is keen on. And I guess one could complain that the name ecumenical is a bad name. I had this conversation the other day because, you know, lots of people tend to think about Christian churches when one talks about ecumenical. But here it's just supposed to mean things that can coexist in peace. And and what Prawitz is saying, this again is a quotation, I didn't put his name, but it's another quotation from him, is saying that that when the two kinds of logicians are discussing this stuff together, they must agree that, that the notion of disjunction that's classical is trivially provable for any sentence, even when it contains intuitionistic constants. And the classical logician, that the intuitionist has to agree with that, even if A and A, not A are kind of intuitionistically valid, but the disjunction being a classical disjunction makes that something that's provable. And the classical logician must admit that he has no grounds for universally asserting a intuitionistic disjunction, not A, even if A contains only classical constants, because there is this fundamental difference between the disjunction that's classical and the disjunction that's intuitionistic. There is an easy argument here from Quine about saying that the logicians are not actually disagreeing so much because they are talking about different things. If there are different concepts of disjunction classical and disjunction intuitionistic, they are not talking about the same object, disjunction. So, so Quine says one shouldn't kind of have to decide between these things. And Prawitz a little bit agrees with that, but not much. And let's kind of see how, so now kind of, let's go back to mathematics, because I feel very uneasy kind of trying to go over this more philosophical grounds. And let's see what we have in our hands. Now, the Prawitz system consists of two disjunctions, disjunction classical, disjunction intuitionistic, two implications, two existential quantifiers. And it has only one negation, one conjunction, one negation, and one constant for the absurd, and one universal quantifier. And the reason for giving this talk today is actually to think hard about why this particular version. As I hope to show you in a few minutes, there are several other similar versions of ecumenical systems. And I think what is interesting, for me at least, is to think about which criteria should you use to choose different logical systems. When is a criteria optimal? How does it how this particular system that is my favorite compares to other ecumenical systems? And which proof theoretical properties does this one have, and which ones do we want to a good system to have? And so, it's very much an open sort of, there are theorems as part of those papers that I mentioned to you, but it's very much to have this conversation about what do we want to have. So, I mean, it's the only reason I have this slide here is to say that we will have rules for the new quantifiers that we're introducing. The old quantifiers are the intuitionistic ones, but the new ones, I'm going to discuss them one by one, and that's the main bit of the talk. But I also kind of wanted to mention this tiny thing here that says that predicates, some of them are going to be classical and some of them are going to be intuitionistic, and they all kind of, the negation kind of gives falsum for both of them. So let's kind of discuss the rules. I hope it's big enough. We want to discuss, first of all, the the classical implication. So I don't know how much you remember about that, but intuitionistic implication is the heart of the intuitionistic system, right? The rule that we have in intuitionistic logic is the lovely rule that says if you have an A and you do a proof and you get to a B, then you can discharge your A and you have A implies B, and that's going to be my intuitionistic implication. Now, that implication does not satisfy some of the stuff that the classical implication does. So in particular, classical implication satisfies not A or B. again, classical or, right? And, you know, there's something fairly different between this and that. One of the things that is very different is that this thing here, it's symmetric, right? You can swap this around whenever you want. Whereas when you're thinking about functions, which is how I think about if you have an A and you prove a B, then you have an A implies B, this thing has a definite direction. You have to be given an A and you have to prove the B, and there's no swapping around in principle. But if you want to define a classical implication, you could exactly, I mean, so this is only classical, and there's other things that are only classical, like, for instance, the Morgan laws. So if you want to define an implication that's classical, you can try to say something like that. If you have an A and you have a not B, and you have a pi that gives you falsum, then you get your A classically implies B. And what's the intuition of that? Well, the intuition is that you want your new classical implication to be something that looks like it satisfies this rule here. So that means that if you have an A and a not B, and you prove a falsum, so that's part of the rule, that's going to be classically the same as not A and not B, right? This is just a definition of negation. And this thing classically will be De Morgan, like not A or not B, which again classically is B again. So you define your implication. Yeah.
Is that pi 1 is just a symbol for some derivation? 'Cause you didn't
Exactly. I could have just put 3 dots.
Gotcha.
Yeah.
Pi for proof.
Yeah, proof 1, you could have 2.
Yeah.
Or-
But you know, you see what I mean, right? It is a sensible way of defining the classical implication, because you are actually asking for the things that you want to be true. And you do the same. It's the same for the classical disjunction, right? Again, as I was saying, the classical disjunction satisfies the De Morgan rules, and the intuitionistic one does not. Then you ask for the classical disjunction to do the De Morgan, so not A and, because you know that's the thing. In these trees, you can only think about ands. You can't think very easily about ors, right? So you have not A and not B. Again, pi 1 falsum, so negating that, and that will be your classical disjunction. And similarly, for the existential, right? You want to kind of create an existential.
Can you go back to the last slide for 1 second? I missed that.
Sure. I have 2 rules here, which
Wait, so
is the elimination side.
doesn't the classical elimination rule for classical disjunction essentially create a new? Wait, no, never mind.
Right. I did not discuss the elimination rules at all. In the first one, I didn't even put it in. But, you know.
I was just surprised to see specifically bottom there, but
Yeah.
it's fine, I think.
Right. I think, I mean, can I just use your not question for a special thing, which is that it's another one of these more philosophical ideas that the introduction rules are the meaning of the connectives, and the elimination rules are just built up to be equivalent. That's part of one of the philosophical theories.
I thought there was like a notion of like positive versus negative connectives, depending on which.
There is a theory of positive and negatives, but I am actually trying to avoid thinking about that at all. So this other one is proof theorists in these days have a collection of new tools on their armor, and I only know some of them, not all of them. So I am trying not to think about negative and positive things, because I think there are many different notions of. and negative stuff around. So, okay, so we have that. That is similar to the disjunction in the sense that I want to invent an existential quantifier that corresponds to the negation of for all x, not a of x, and that's what the introduction rule does here. So here is the full system and all the rules that I did not present. So there are some rules that are intuitionistic, which are the introduction of implication, the disjunction introductions, and the well, what am I doing here? Oh yes, because, sorry, I have two existentials, two disjunctions, and two implications, right? So these are the intuitionistic rules. These are the rules that are shared, meaning the conjunction is shared, and the introduction of the negation is shared, and the introduction of the universal is shared. And then there are the classical rules that we went on one by one, I hope. Yes, we did these three. So that, yeah, go ahead.
I'm curious, can you talk about the intuition behind the conjunction could be shared while disjunction could not be shared?
Yeah, I mean, it's a traditional idea that the conjunction can be shared because there's nothing specifically important about witnesses for conjunctions. But for the disjunction, the disjunctions are very different, right? The disjunction that's intuitionistic, you need to know which one of the branches is true, whereas for the classical disjunction, you don't have to know that one of them is true. You know, you could just get it from the general shape of the rule by using the negation in total. So, yeah.
I think one salient fact which may or may not help is that intuitionistically not distributes over conjunction but not disjunction.
Say again.
Double negation distributes over conjunction but not disjunction intuitionistically. Like that is a very concrete, formally true fact, which is relevant.
Right. I don't think I want to go over distributions quite yet, but I actually have a slide about that kind of later on, which I don't think, at least to me, it doesn't help very much. But I think what is good about your question for me, Hannah, is the fact that first thing that you could say to yourself is, okay, maybe Prawitz convinced you that you should have different connectors for intuitionistic and classical. And then you might say, well, then why don't I have both conjunctions, both disjunctions, both implications, both existentials for each one of them? And the idea here is that you're trying to minimize the duplication of rules because having too many rules might be bad for you. Yes?
I think another way you could put it is that you could make there be a classical and an intuitionistic conjunction separately, but they turn out to be the same thing. And actually, this is related to positive versus negative.
Sorry, I didn't.
This is related to positive versus negative.
Conjunctions are negative types and disjunctions.
Okay, fair enough.
Yeah,
It's one version of positives and negatives, yes.
Yeah. Anyway, sorry.
Another interesting thing, the universal and existential introduction rules are the same in your notation. I guess like A is a random term in the universal introduction, and A is a specific term in
Yeah.
the existential introduction. I'm not sure how like you actually say that properly though.
You always have to kind of keep those sorts of side conditions on, right? You know, you cannot get rid of it. Hang on just a second. Professor Scott had a hand up. Are you going to say something?
Well, but finish your sentence.
Oh, no, I was just saying that I think side conditions are necessary in any case. We have to have them.
Yeah, but I think the one for all is just wrong. Like you don't want to.
It could be.
Free variable.
I just copied somewhere, so I don't know what exactly.
Have you compared these thinking with the algebraic approach with lattices? Does that help this, you can think topologically. If you have a topological space, then the Clopin sets that are both closed and open form a Boolean algebra, and you have all the laws of classical logic. But if you just take the open sets, then you get the laws of intuitionistic logic, as a lattice of open subsets. But particularly nice, as Tarski, a long time, pointed out, others too, that intuitionistic implication as defined in the lattice of open subsets comes from the fact that conjunction in open sets, of course, the conjunction of two open sets is open, and the union of arbitrarily many open sets is open, and conjunction distributes over union.
Right.
And so you can use that insight in order to see that in any hiding algebra, you take a complete lattice, and then implication is defined as P implies Q is the largest proposition such that P and R implies Q.
Right.
Modus ponens is somehow the characteristic of what defines implication. Implication is the largest proposition, or in a lattice would be the union of all the open subsets, such that P intersected with R is less than or equal to Q. And so that corresponds very much to the way you use some of the deductive rules. Here.
Right.
But I think the topological interpretation also, as you know, for modal logic, does help you kind of see what structures are possible when you think of it in terms of lattices.
Right, and I mean, it's true, all true. We know and love that bit. I mean, that's why we like algebraic logic and stuff. But it's not what is kind of why I'm kind of worrying about that right now. Because in particular, when you start thinking about things like linear logic, the distributivity is not there anymore. So you're kind of talking about slightly more, we want to think about things in a slightly more general setup, if we can. And hence, I reckon, and again, you know, it's this business of separating the two different kinds of conjunction that we have in linear logic. So hold the thought. Let's think a little bit more about it in the continuation. So this system that I described as being Prawitz system, he describes it in 2015, and Pereira, my friend, and someone called Ricardo Rodrigues, they codified the propositional side, and they proved most of the things that you would, I mean, since it was created to prove these things, you hope that they would prove. So it does prove that intuitionistic implies the classical implication, and you have lots of double if and only ifs that are intuitionistic, like the De Morgan laws, kind of here, and some sort of part of the De Morgan laws for the quantifiers. Now, one of the things that they show, just a sec, is that that there is an interderivability in terms of the negation can be a single negation because you have some sort of interderivability between the classical implication to falsum and the intuitionistic implication to falsum, which is the next thing that I want to discuss. But yeah, go ahead.
I was just curious, do you have anything like I implies B, classically implies A, classically implies B?
Yes, because everything that you have intuitionistically, you have classically. Isn't that what, I mean, I don't know if I got your...
like if you have an intuition...
what you cannot have, and...
Oh, wait, no, sorry. No, yeah, I had it backward. I meant the other way around. Like does a classical implication allow you to derive a stronger result because it can't tell the difference? Like, can you say, like, if you have
No.
A classical or B, does that classically imply A intuitionistic or B?
No, of course not, because there is a difference between the two
Well,
systems.
yes, but if it's a classical implication and not an intuitionistic implication.
Ah, right. I don't know. I know that some of the obvious ones
I was curious. It's okay.
work or it don't work. So, of course, you have the excluded middle classical, but not intuitionistic. Of course, you have double negation classical, but not intuitionistic. And most annoyingly, for lots of people, you have modus ponens working intuitionistically, but not classically. Sorry, intuitionistically, here it should be, yeah. It does, you could have a classical there as well, and it doesn't work. So some people would say that this system, and as I was saying, that's the point of this talk, is kind of how do you choose the system that you think is the best one. So some people would say, oh, if you don't have modus ponens for classical implication, then this is a bad system. I don't like it. Some people do say that. But in general, it works the way you expect it to work. That's why you build the system. And the properties that we have are things like we have normalization for the propositional fragment and for the first order fragment, but it was not proved in the first paper. You have soundness and completeness with respect to a cryptic style semantics. The paper that I joined in then shows that we can also define a sequent style calculus corresponding to the natural deduction that we've been discussing, and they could prove cut elimination for this calculus. And my colleagues, the two that I showed pictures of, they carry on doing lots of other work on that. So they added modalities, they added stoop, they have lots of other things. But as I was saying earlier on, what I wanted to discuss with you guys is which properties do you want of any decent logical system? And I'm giving my list, my desiderata list, my laundry list. I'd like to have always Hilbert, sequent, and natural deduction presentations shown equivalent for any logic that I think is worth the name logic. I'd like to have normalization in the natural deduction version. I'd like to have cut elimination, preferably with subformal property. I'd like to have Curry-Howard terms and subject reduction, confluence, and a few other bits. I'd like to have, as Dana was saying, related, meaning I want to have algebraic relation and categorical semantics related to each other. I would like to have interpolation. And last, I would like to have good properties of the rules, which are the properties that I say the proof theorists have been talking about. So things like that they call harmony, separability. There's a third one that normally they talk about. Purity of the rules. So these are things that are good. Don't get me wrong. But to me, it's the last of my personal list of desires. And as I was saying, I think you kind of saw it before, that we do have this, and this for the system that Prawitz introduced. We don't have Curry-Howard, and we have relation semantics, meaning cryptic semantics, but we don't have categorical semantics, which is the reason why I'm giving the talk here, because I want people to think about that. And not even algebraic, because you want to have Heyting algebras and Boolean algebras kind of related in a special way, if we can. And of course, I would like to have the other ones too, but for me, these two bits here are kind of quite essential, and that's why I want to carry on working on that. Now, you might say, what is happening to Curry-Howard? What happens? And Emilie just defended her thesis in February, that's 2025, and her thesis is called Combining Computational Theories, and she has a different ecumenical system. She calls it ecumenical too, that's why NE, but instead of duplicating only disjunction, implication, and existential, she duplicates everyone and has subscripts I and C for everyone. She adds a third connective that embeds the formulas for the intuitionistic and classical separately into her system NE. Like Prawitz, she has a single negation, a single true and a single false. And she developed some sort of ecumenical type theory. And she connects this type theories to the lambda cube of type theories, the Barendrecht cube. And the reason she does that is because she wants to use these theories as computational theories for deductive and rock. But there's a problem with that. And the problem is how good is the proof normalization that she has. It's very much based on notions of equivalence classes, and hence life is hard when you try to think about things in terms of equivalence classes. The syntax goes completely difficult, and I don't know how good this one is. And as I was saying, my collaborators, Pereira and Pimentel, they have many more proof theoretical properties in mind. They want purity, separability of rules. They kind of want to use polarities. And they kind of really only care about crypt-like semantics, which I'm calling relational semantics. And they also want, which I think is very reasonable, if this stuff is going to be a good way to put together intuitionist and classical logic in a single system, then you should be able to put the modalities too. So they do have Simpson-style modal connectives, which again satisfy the things that we were talking about early on, that we discussed about keeping the conjunction as being the same and doing the other. So when you get to, everyone knows that the quantifiers are similar to the modal operator, so the box is like the for all, and the existential is like the diamond. So you have two different diamonds and just one for all, so just one box. And I kind of wanted to finish off with this sort of a problem for me, which is that I find it very surprising, strange, that we have two implications, one classical and one intuitionistic. And the negation of a proposition can be understood as A implies falsum, but we only have one negation. And we only have one constant for absurd. So why don't we have a negation classical and a negation intuitionistic? And that's the last thing that I want to say, because we are getting late here. I wanted to show you this interderivability, because I think that vaguely sends us back to something that that Dana was talking about, distributivity and stuff like that. So if we want to prove that A intuitionistic implies falsum if and only if A classical implies falsum. So how do we do that? If we have as a hypothesis A, and you have A intuitionistic implies falsum, then we have falsum by modus ponens, traditional modus ponens.
No. It's so much simpler. Imp sub C is not A or B, and so it's not A there already. So implication classically is not A or
B.
B.
Yeah,
yes,
that's.
But
so
we're worried
you
about
already have not A there, and so you have not A.
Or A
is
is falsum.
Is the intuitionistic implies false. So.
Correct. But I prefer to think about it in terms of this and modus ponens, because I want to see that I want to see the hypothesis that we are getting. So I use modus ponens here, and then I discharge the A, and then I have exactly this implication here. The thing is, in class, we are trying to be as little classical as we possibly can, Dana. So we want to be as constructive as we can. And the bottom bit is a little bit more complicated because you can do, I mean, you need to use the introduction rule for, you have to use the rule that we invented for implication classical implication. And for that, you need to have, I mean, sorry, forget about the tilde here. You need to say that, you remember, the rule for implication is not A, no, A and not B proves falsum. That is the way to create a constructive implication of A implies B, right? I have to have an A and not B. I discharge the things, and I get, that was the rule I showed you at the beginning, the main one that we spent hours discussing. So I need to have, in this case, the not B, so the not falsum, to connect, to discharge, to fit in the rule model that I gave for implication. And then, and from that, I get falsum, and from that, I just kind of get my discharging the A, I get the intuitionistic one. I'm actually using the A. And you might say, well, Valeria, but then aren't you cheating here? Because, you know, this rule, I mean, I wanted to prove A classically implies falsum, implies A intuitionistically implies falsum. I do have this as a hypothesis, and I do have this as a conclusion, and this hypothesis was discharged, but this one was not. So why this still works? And it works because not falsum is not a hypothesis of this proof, because not falsum is a theorem. It comes from nothing. So I have this interderivability. And again, thinking about how to generalize that for other systems, I have to think about how to change this proof. And I think and I don't know. So I have some possible ways of dealing with stuff, some of them including the Glivenko theorems, which I think can say something about it. But again, I cannot categorify any of this stuff. So summing up, I have some good reasons for one negation. Interderivability. I have a lot of philosophical things from Prawitz on assertability conditions, and also it works. But it leaves plenty of interesting problems. And you know, the question remains. There are many different ways of putting together classical intuitionistic reasoning. Which one to choose and why? And with that, I'll stop. Thank you.
So much.
Sorry about that. Fine. You guys.